how often do you get to see research, really cool research on math? You might think, oh my goodness, that doesn't happen. It does. And let me show you. So this is a chapter in a dissertation for a student of mine. Her title of this paper is Optimal Additive Dose Distribution for Minimizing Dose Estimate Error and Retrospective and Emergency Dosimetry with Heteroscedastic Errors. So you're like, what in the world? That's a bunch of gobbledygook. Well, let me simplify it for you because this is really cool. If you like math at all, you're going to love this. So the idea is if I have a linear response, I measure something with a linear response. That means that I've got basically some kind of data like this. So I've got a response here. This is going to be dose. And this is the signal that you get as a function of dose. And so you're going to get some kind of data points, and you can fit a line to it. So there's the crux of the issue. Fitting a line to data. So I have a bunch of linear data, and I need to fit a line to it. Say, what's the best fit to that data? Now, to start off with, you got to define something called a residual. The residual is basically the vertical distance from a data point to the fit. So sometimes it'll be negative, and sometimes it'll be positive. And the sum of the residuals have to be zero. That's a necessary but not a sufficient condition for the optimal fit, because I mean I could get a line that was, you know, perpendicular to this and I'd still have the sum of the residuals be zero. So that's important, but what we do to get the best fit is we do the sum squared of the residuals. So here's an approximation of the formula where you're squaring all of the different terms. So each residual, that's the distance from the data point to the fit, and that's each residual, and you're squaring them all. And the best fit comes when you minimize that. So you minimize the square of the residuals. It takes a lot of calculus. You do the calculus. But the point is all right, then you figure out what the best fit is. What's the line that best fits the data? Now, all of that math that we use, you might not realize this if you've ever done linear least squares, is you have to assume that all of the errors, the variations there are normal. They're Gaussian. And that they're the same. Unless you do a weighted uncertainty where you weight them individually, but normally, a normal least squares, you just assume all the data is normal and then you fit it. But what if the data is not normal? What becomes the best fit? That becomes a bit of an issue. But in the topic that she picked here for retrospective dosimetry, the key metric that's being optimized is the extrapolated distance back here. Because if I'm doing retrospective dosimetry, then if I extrapolate how far back does the x-intercept take place, that's the dose. That's historical dose that somebody's had. And so the question is, how do I minimize that extrapolated uncertainty? So if I project out, I project this line, and I say, all right, so there's going to be some projected uncertainty here. Can I minimize this uncertainty by how I decide to space these data points? That's what she figured out. If these data points are spread out in a different way, and I have specifically not homoscedastic uncertainties, I have heteroscedastic uncertainties. That means that my uncertainties are all completely different. They could be like relative and constant or Poisson. And specifically, they're a mix. They're mixes of different kinds. Like, for example, a relative uncertainty, to put that in context, means that, let's say I had relative uncertainties of 1%. If I had a signal intensity that was 1,000,000, right? If I had 1,000,000, that's really big, then that means that my uncertainties are going to be about 10,000, right? 10,000 is still a big number, but it's small compared to 1,000,000. But if my signal is down to, say, 100, then the uncertainty is 1, because it's a 1% uncertainty. So it gets really small at small values, but it gets bigger for big values, even though the uncertainty is always 1%. And so I could have that, and I could have some constant uncertainties, say from calibration or something like that, or Poisson based on counting statistics. And so if I have mixed uncertainties, how does the optimization of the dose points change? So what was figured out before is if I have homoscedastic uncertainties, how do I optimize the data points? And it turns out it's going to be a function of how far you're extrapolating back and the intensity of the signals you have there. The idea being to minimize that propagated uncertainty, that was figured out more or less in closed form if I have homoscedastic errors. But if they're heteroscedastic, like basically all instrumentation measurements are, in some way or another, they're all heteroscedastic, how does it change? And that's what she worked out, is that it's similar, but there are some caveats, and she worked it out here in this paper. That's there. And it's going to be a chapter in her dissertation, so she's brilliant, no doubt about it. And there's the reference. So I hope you like it. It's really cool stuff. I mean, how often do you do math research, right? Exciting math research. Anyway, I hope that you all learned something, especially about linear fitting. It's very cool stuff. Maybe some statistics. I don't know. But thanks for watching. Hope you have a great day. Bye.